All right, guys. So today we're going to talk about nuclear chemistry. We're going to talk about radioactivity and radioactive decay. These are our objectives. You should understand that a nuclear reaction occurs in the nucleus of the atom. Understand that elements can change in a nuclear reaction. Understand why chemical reactions are different from nuclear reactions. Specifically recognize alpha and beta particles and decay. Recognize nuclear reactions based on their equations, and you're going to predict products or reactants of nuclear reactions based on equations. Couple of key differences of chemical versus nuclear equations are right here. So chemical changes, they occur in the electron cloud. We have atoms, nuclei remain intact. The nuclei themselves are unchanged. Elements in the beginning are present at the end, and mass is conserved. In a nuclear reaction, that occurs in the atom's nucleus. The atoms are changed. We have new types of atoms because their nuclei are different. And new elements can be produced that were not originally present. Mass can be gained or lost, and that's where we come up with Einstein's famous equation, E is equal to mc squared, where energy is equal to mass times the square of the speed of light. So that is the mass that's lost is converted to energy. Here's a couple examples of chemical reactions versus nuclear reactions. The first one, magnesium plus hydrochloric acid makes hydrogen and magnesium chloride. Notice we start with 1 magnesium, 2 hydrogens, and 2 chlorines in the reactants. In the products, we have the exact same numbers of each element. A nuclear reaction, for example, this one, the beta decay of sulfur 35. We start with a sulfur atom, we end with a chlorine atom. We have a different type of element that we created, a new atom that wasn't present in the beginning. Okay. So just a quick review on isotopes. Isotopes are a variation of an element. They're a specific type of atom, chemically identical, but physically different in that they have different mass and different numbers of neutrons. So these are 2 isotopes of chlorine, chlorine 37 and chlorine 35. Their average atomic mass is 35.45, which we discussed last unit. And what do they have in common? They have the same number of protons, the same, and therefore they are the same element. Because as we've discussed before, we know protons is the atomic number which defines the element. So how are they different? Their mass numbers are different because they have different numbers of neutrons. So that's it. And that's why they have some different physical properties. Not all isotopes are stable. So we have carbon-12 forming, but never carbon-11. Certain isotopes, certain elements only have 1 isotope, like fluorine. There's only fluorine-19. Some isotopes are extremely stable. Others are radioactive, meaning they aren't stable forever, and eventually they will decay. So here's a little chart that outlines what the couple different isotopes for certain elements. So we have hydrogen 1, hydrogen 2, and hydrogen 3 by the mass number. Helium only has 1 stable isotope, that's helium 4, with 2 protons and 2 neutrons. Excuse me. We have carbon up here, which has 3 isotopes, carbon 12, carbon 13, and carbon 14. And you can tell we have lithium here, which isn't filled in, has 2 isotopes, lithium 6 and 7. Beryllium has beryllium 9 only, and boron has boron 10 and 11. We get those isotopes because we find the mass number by adding up the protons and the neutrons. Okay, so helium has 1 isotope, lithium has 3. This is a little extended version. As you can see, one thing I do want on the horizontal axis, that's actually number of protons. You can see by the elements up there. And this line here represents 1 proton per 1 neutron. And as you see, the larger the substance gets, the larger the atom gets in the nucleus, the more neutrons we need to keep it stable. Okay. So in the smaller ones, you only need an average of about 1 proton per neutron. But as you get bigger, up around 40, you need about 50 neutrons for 5 neutrons for every 4 protons. And as you get even bigger, around 80, you need about 3 neutrons for every 2 protons. So you need more and more to balance out that strong, that repulsion of the protons. So, so we're going to watch a video in a little bit, but we're going to talk first about 2 specific types of radioactive decay. So why do we have radioactive decay? It's because we don't have a stable ratio of neutrons to protons. So if you're too large, you're likely to go through beta emission. And if you're too small, you're likely to undergo alpha emission. There's a couple more here that we're not going to talk about. And we also have non-radioactive isotopes, which are perfectly stable. They're a stable form of the atom, which will not change under normal circumstances. So we'll watch that in a sec. Alpha and beta decay are 2 specific types of radioactivity. An alpha particle is just a helium nucleus with 4 mass and 2 protons emitted from the nucleus. A beta particle is a high energy electron emitted from the nucleus. The origin is a neutron in the nucleus that becomes a proton and an electron. The electron is shot out into the outside of the atom. And there are more that we're not going to cover in this class. We have positron emission. We have a whole bunch of different more. Electron capture and stuff like that, which are also interesting. So here's a little chart. Alpha particles. This is the symbol that I use. You might see it as an alpha, the Greek letter, which I'll talk about momentarily. It is the larger of the nuclear particles in this type. You may have remembered those from Rutherford's gold foil experiment, where he shot the alpha particles at the gold foil, and some of them bounced off the nucleus of the gold and going right back, bouncing right back. And that's how they discovered the dense nuclear model of the atom. Beta particles are high energy electrons. They have slightly higher energy. They're effectively their size of radiation. And they have a good amount of energy, and they can be dangerous. Gamma radiation is a high energy released from the nucleus based on the reorganization of it, and it's high energy and can be very dangerous. So, but a lot of times there's a lot of nuclear reactions going around all the time that we don't even recognize or know about, just because it doesn't happen in a large amount. We just kind of ignore it. A couple cool things that you might see are your smoke detectors use radioactive particles to work. So there's an example of radioactivity that's going on in everyone's house right now. So alpha decay, I'm going to go over this example. I'm going to take the iPad and I am going to share my screen. And I'm going to go over the alpha decay of uranium-238. So we have an alpha decay. The alpha decay is of uranium 238. So alpha, an alpha particle, I'm going to write the Greek letter alpha. There we go. That's a Greek letter. It's the first letter of the Greek alphabet. And it is a 4-2 helium nucleus. Okay. So we start off with uranium 238. I'm going to do the mass numbers in blue and the atomic numbers in red. So we have 4-2. It's alpha decay because it's breaking apart into something else. So we have to figure out what's left over here. What is left over after I give that up. So first thing I do, I go over and I take a look at the atomic number of uranium on the periodic table. So I looked that up, and that is 92. Okay, so now I figure out what's missing. So from the numerator up here, we just fix that. There we go. There we go. The numerator, if I have 238 and I give up 4, I'm going to be left with 234. And in my nucleus, if I've given up 2 of the protons, 2 atomic number, I'm left with 90. And I can look up atomic number 90 in on the periodic table, and we find that it is thorium, TH. Okay. All right. So let me go share the screen. So the next example is an example of a beta decay. So that was our example of an alpha decay. Sometimes you'll see the helium nucleus written as alpha, but that's I won't do that. I will always write it as helium 4-2. Okay, now the beta decay, here we have an example of beta decay of cesium-137. I'm going to go talk about that. So we have the beta decay of cesium 137. 137 is referring to the mass number. So a beta particle that looks like that's the Greek letter for B, the second letter of the Greek alphabet. And a beta particle is 0, -1 e. It's that high energy electron. So we're looking at this. We want to see what the product is. So if I have cesium 137, let me color code that. And I give up a beta particle, 0, e, -1. I want to figure out what's left over. Okay. So first I look up on the periodic table that cesium has a atomic number of 55. And in this way, we can kind of think about this like a mathematical equation. And I love the beta particles because they're so easy, because the mass doesn't change. So if I have 137 and I've given up 0, I'm still going to be 137. Now, I need to figure out what number plus -1 equals 55. And that number is 56. So 56 plus -1 equals 55. So now I take a look at my periodic table and I get to barium, Ba. is the chemical formula for barium. So that's what we're gonna do today for notes. So I'm gonna stop this. Here we go.